Okay, after our last talk for the day, there will finally be coffee again in the same room as before. And we'll also have some time then to discuss the question from German's talk and maybe also from Thomas' talk. And hopefully tomorrow the air will be better in here, but the air conditioning is turned on again. And then we start our last talk mapping the third exact sequence analysis.
Yeah, thanks a lot for the invitation here. Looking forward to give this series of 4 talks where I try to put an analytic aspect to this whole surgery story. And let me describe to you some of the goal of most of these lectures. So it's a simple one. Namely, we have the surgery exact sequence. And try to understand something about it. That's it. So, the surgery exact sequence was maybe for me to have non-empty sets, fix a closed, and I'm always in the smooth category. So some stuff can be done in other categories, I'll talk about that. And I think a close oriented, smooth M. And we'll later have the reason to kind of focus on the fundamental group, and there's a base point to be chosen once we do that. So there are some issues here, but let me sloppily say the fundamental group I call gamma. Authority most picking the base point, of course. The good thing, this M is going to be the Poincare space we had seen before. And the good thing is, if I know it is a closed or smooth manifold, there's at least one element, a smooth structure set. Which one? Yeah, who knows? You know. The identity map is an element structure set, so we do not have to worry about empty structure sets, which was one of the things which is a bit degenerate in the sequence, which can happen. Well, so that's just making this. And then we want to understand, I'm skipping the diff, because I fixed the diff category. We want to understand all manifolds which are homotopy equivalent to M, up to the equivalence relation, which is built into the structure set. And again, I should fix the simple or non-simple homotopy equivalence stuff here, but I'm going to have a map which requires inverting 2 in the end, and then all these issues disappear anyway. So let's skip that too. And understand this. And we know the surgery exact sequence tells us something about this in terms of these normal invariants for M. And let me put the dimensions here instead of a diff, room for that. And the L group, of course, geometrically defined. And we also saw that this extends to the left. And here was a discussion that these are clearly groups. Here it's less clear, it's quite unclear. And this map is, they're not homomorphism, but actually an action. And that there was a definition of what it means to be exact in this case. And then I'm not going to say too much about that, but this extends to the left by crossing M with the interval and then look at its relative structures relative to the boundary and go on all the way to infinity to the left. Okay, so the goal is to take this surgery exact sequence and map as an exact sequence to something else which we have some information about. I mean, I don't know whether we learned so much new about it, which we couldn't learn also by looking at the surgical sequence, because we know there's quite a lot we can say about that. We saw in Demos talk, a lot of calculations are really doable. Still, I think it's always good to connect different parts of mathematics, and so it's worthwhile to map with non-zero maps to some comparison thing and map to C star algebra K theory. So now it's pre-splitted in this box, but this is the new player which I somehow want to bring in. I want to map the C star to K theory, and I want to do this rather directly. We have seen for all these spaces a cycle model, so we can take representatives which are mainly, now M is a smooth manifold, they're consisting all of smooth manifolds and maps between those, sometimes with, sometimes without boundary, and sometimes with different conditions on the maps. So I want to take such a cycle, and I want directly from that cycle, as directly as possible, produce something on the bottom. So not some trickery with wiggling around a lot to make the cycle here in a very nice form, and then just map it on the nose. And this will be achieved by using indices. I'm talking about that of the signature operator on the manifolds we have in our cycles. Okay. And where do we want to map to? This is now going to be a sequence of K-theory groups of C-star algebras, and we have certain C-star algebras which are associated to the situation. And so we have here a K-theory group of a C-star algebra D star of M. So to be more precise, let me write it like that. So it's associated to M, but it works through the universal covering. That's at least one way to do that. So we will have to take these non-compact spaces into account. Here we have the K-theory of M modulo ideal C star of M. And here we have the K-theory of C star. So I have later on to explain these algebras, of course. And you see the two, and they seem to sit one on the other, and we can form the quotient. And indeed, we'll talk about C-star algebra K theory. Each time you have an ideal in a bigger algebra, you do get a long exact sequence of K theory groups. So this actually extends as it should. We're going to now about should get the.
Does K theory has index?
Fun?
Index. Like which dimension K theory does it have?
That's what I'm writing down precisely now. So stay tuned. Here. And then there is actually a miracle happening. So what I want to do is to define this sequence of K-theory groups, and then I want to define homomorphisms, whenever these are groups, from the top to the bottom, let's say maps, such that the diagram computes. And indeed, to do that, at least if you want to go to the left, it really is necessary to invert one half, which I said I do. So that's just censoring Z adjoins 1/2 as a ring. And indeed, once I've done this, I have not to worry anymore about the declaration of the homotone stuff we've seen. So that's another reason why we can do that to get the safe side. Well, one thing which is hopefully a nice piece of information for topologists is that this in these, on the K-theory side, this is something we should know and love. This is canonically isomorphic to the K homology of the space M.
But on the K-theory side, you also invert 2, right?
Yeah.
Or,
I mean, once you build 2 here, you certainly can't map to a target where you haven't built 2. That's true.
What does inverting 2 mean in the top row of the things that aren't groups?
Once again,
What does inverting 2 in the structure set mean?
you caught me. Okay. So, and I guess what I should have said is that once I inverted 2 here, I really don't care about 2 torsion phenomenon here. So it is of course something which is defined, or it's actually something which is defined on the notes, and it still doesn't depend on decorations because it mapped to something where 2 is inverted. So the defect here wouldn't be seen in the target in the map. So we are, yeah, that's a better way to phrase it. I mean, better in the sense that it's making sense. Very well. So here this is K homology of the space M, the homology theory dual to K theory. There's a little degree shift here. This here is also the value of a generalized homology theory on M, the L homology, and this map is really a map of homology theories, which we actually know the map from L theory to K theory over this point. Okay, so once again. Goal, and let's perhaps start slowly by talking about this mysterious signature operator. Okay. So let's make a test. Who has not seen the signature operator? That's a differential operator. One person, all others have seen it. So what is a signature operator?
You asked whether I'd seen it.
Maybe it's worthwhile to talk a little bit about it. So we have this smooth manifold M, and I'm fixing a Riemannian metric on M, and now stuff works even, so a lot works if MG, this metric is just in the back, we don't really need much of it, it's just complete. Not necessarily compact. This is good news because at some point we pass through this universal covering, which is typically not a compact manifold, but certainly a complete one. Okay, so, and we have this orientation. So that gives us a lot of things. So one of the things we have is the differential forms. Of M, so smooth differential forms.
Can I ask one more question?
Of course.
So you said this map is really just this map from L theory to K theory. So does this at every point factor through the topological surgery exact sequence?
Yeah, so indeed, Tozenobi just checked that one can make the definition of this signature operator-based constructions for topological manifolds using a heavy hammer, namely the fact that every topological manifold has a Lipschitz structure, so there's a little bit of differentiability available, which allows you to do the index theory, and the whole thing factors through that.
And it's an explicit computation that then the map from the normal invariance is really the Sullivan orientation. And from the G1 top to B.
Maybe let's say this is very much expected. Okay, so what we do have are differential forms and the RAM operator. So all of us know that. And that doesn't use a metric, of course, but the orientation and the remaining metric will also give us the Hodge-Star operator. M-dimensional, that of course implements Poincare duality on this analytic level, and then we can put these two together. Actually, would not require orientation really. We also get inner product on at least the forms with compact support. By L2 in a product, by integration over the manifold, the inner product you can carry out in each fiber, just coming from the metric on the tracing space. It defines a scalar product fiber-wise on the exterior algebra bundle fibers, and then fiber by secondary product, and we can integrate against the volume element coming from the metric. Defines an L2 in a product, and L2 forms are defined with the completion of the compact supported ones with respect to this inner product. Now, it does. Having an operator and an inner product, we can ask for the adjoint operator, at least formally, and there is the adjoint D star of the decreasing degree by 1, and actually can be computed using the Hodge-Star operator. It's plus minus, which depends on the degree of the form, star D star. Easy. And now I'm defining the signature operator, leaving out the most important bit of information that comes in a second. The signature operator is just D plus D star. And well, what does it do? It maps from the direct sum of all form degrees put together to itself. And things are clearly getting mixed up because of some E and star. This, however, is not a very exciting operator. So far, we need one extra bit of information to put in. We also need the so-called signature grading, so that's all together really defining the signature operator. The two only play together. Grading. And grading means a C2 grading. So we have to split our differential forms into two parts, an even part and an odd part. And we don't do even degree forms and odd degree forms. That would be the wrong grading, not the signature grading. We put in the Hodge-Star operator once again. Actually, here it's not really needed. That's just a convenient way to write down the adjunct that exists without having Hodge-Star. But here we definitely need the Hodge-Star operator, so that's where the orientation really is used. So the grading is, I know, in, let me say, plus forms and minus forms, and they're defined to be as kind of lowest standard gradings, the +1 and -1 eigenspace of a certain involution, and we call it tau. If you well write down this involution tau, +1 eigenspace -1, -1 eigenspace +1, and tau is essentially the Hodge star operator. Well, it has to be an involution, so applying twice it should be the identity. If you check star and Hodge star is giving you ±1 depending on degrees, that can easily be fixed by multiplying it with an appropriate power of I, the square root -1. I to some epsilon, this is ±1 depending on degrees. And I didn't look it up, it's not really important for us, but you can do it in a consistent way to produce this grading operator here. It's essentially a star operator, which lets us split our form space into a plus part and a minus part, which clearly are preserved by B plus B star. So a little exercise on those related. Very easy one is that tau the sig is minus, so the commutator or the anti-commute, the signature grading operator and the signature operator itself.
So you are always assuming that the dimension is even? Or
I have to admit here that I decided, I should have said this earlier, for simplicity of the presentation, to concentrate on the case where the dimension is even divisible by 4, at the moment. There are versions of the signature operator in all dimensions. Unfortunately, I don't really know of a presentation which is uniform, so we just do the different cases. And then we fix this one case that we want to concentrate on. Okay? So once again, signature operators exist in all dimensions, and I want to concentrate on, assume now that M is divisible by 4. The fact that really there are different formulas and it's not so uniform is one of the reasons why it's almost inevitable to somehow run into trouble with a factor of 2 business if one compares different dimensions. Okay, so consequently, the signature operator, if we write it as a matrix according to the splitting of our forms into plus and minus part, looks like that. That's the signature operator. Now, you should ask me or yourself, why is it called the signature operator? What does it have to do with the signature? And it's not so hard a proposition that the signature, and now we're again in a situation where it's good that the dimension is divisible by 4, so that's fine. The signature of M, which is the signature of the intersection form on a middle degree homology. We haven't seen it, but in studying in this surgery problem, the signature is a very important layer. So it's no surprise that we are using it for our map out. And the signature operator is a signature operator because this number is equal to the index of the signature operator, which by definition is nothing but the dimension of the kernel of the plus part minus dimension of the minus part. Okay. And again, maybe that's an exercise to prove this. Using, of course, we watch theorem, which in particular says that the cohomology of our manifold is isomorphic to the kernel of the Laplacian, which is the square of the signature operator. Which, by the way, is the same as the kernel of the signature operator itself. So the kernel of the signature operator is showing up as the cohomology. The signature is somehow measuring something on the cohomology, and we look at this precise combination of dimensions of kernel parts. You just get the same thing. Okay. So we're going to, I guess this is if n is compact. So the rest of the stuff is for non-compact manifolds. I guess this is compact. Right. So this implies implicitly, well, to be able to be true, these two statements, of course, means that on compact manifolds, this differential operator, signature operator, has a finite dimensional kernel. So somehow to be able to do this index theory and more refined versions of it, we need to know quite analytic properties of the signature operators are necessary to be known. So that was next thing I want to talk about. Let's do this. Operator, and most of what I'm saying will be on a complete So, analysis here is easier without boundary. I will not at the moment cover the case that we have a manifold with boundary, although those are going to show up at some point as well, as we saw from the description of the cyclic sequence. And the foremost one is that this has a proposition or a theorem, I don't know. The signature operator is an elliptic differential operator of order 1. Now, I guess we shouldn't be too scared about differential operator. What does it mean to be a differential operator? So, everyone's silent. Frank, what is the reason?
Map of, let's say, different functions, lowest degree, lowest differentiability, right?
Well, if we start with smooth ones, then there's not much to lose, but indeed. So a differential operator is after, so here we map differential forms to differential forms. These are sections of a vector bundle. So if we choose local utilization of the bundle, they really look like vector-weighted forms. And if we choose a chart, a local anyway, they look like maps from Euclidean space to the vector-weighted functions on Euclidean space. Choose a factorization of the bundle and a chart of M. The thing we act on are vector-weighted functions on Euclidean space, and the differential operator is what you expect, it differentiates. And if it's differential operator of order 1, it differentiates only 1. But it's a PDE partial differential operator because we have a lot of directions to choose. Okay? It is on the form. Sum, we have differentiation in the different directions, and well, differentiating a vector, then we can still multiply actually with a matrix value function which mixes the different components. So these are some A of X and matrix value 2. And here everything is smooth. Okay? So that's what the differential operator for the 1 is. Now we could have an exercise, what is it to be for the 2? Work this out now. And now comes a slightly more sophisticated concept. What does it mean to be elliptic? Elliptic means that if we replace the differentiation by just a vector, psi I, so looking at and I guess here I made a mistake. The differential operator of order 1, of course, also has some order 0 part to it. No, which is in this case just one other matrix value function with which you multiply in higher degrees than would be the order 1 part or the 0 part on top of the order 2 part. And the principal symbol just picks out the top order part, throws away the rest, replaces the d by dxi by xi i's. So this is the vector psi. This is now x. So also depending on x, obviously. Right. What do we get for each point? On each psi, we get a matrix. It's a matrix value function depending on the vectors psi. And we want that this function is always invertible as long as the psi isn't the 0 vector when it's 0, so we're not invertible. It's homogeneous in psi, and we want that this is an invertible matrix for all vectors psi and 1 equal to 0. Okay.
So strictly speaking, the matrix depends on the coordinate chart that we use, right?
Yeah, but the property of being elliptic doesn't depend, and one can turn this into actually invariant construction using sections of the pullback, the endomorphism of the pullback function, the cotangent function. That size are the secretly covectors of the cotangent function. So another exercise, find the invariant combination. The principal symbol is a section of the pullback of the endomorphisms in the first and the second bundle, pulled back from the manifold to the cotangent function. Okay? But we don't really need that to understand it or not. So, yes. That, I guess I stated it. So, that is an exercise. Proof that the signature operator is indeed elliptic. And I think it's slightly easier to prove actually better work with the square of it, which is Laplacian. I don't know whether this makes it so much easier, but then the symbol is matrix, but it's really given by the identity operator on the form bundle multiplied with the norm of the co-vector in the cotangent bundle X, which has a norm because it is a Riemannian manifold verb. Okay? And if you see this, you believe that this operator is invertible except if psi is equal to 0. And of course you can check that if you square the operator, you really have to square the principal symbol as well. So invertibility of one is equivalent to invertibility of the other. Okay, that as discussed. Ellipticity is a great property of a differential operator. You really can be happy if you get this. Let me draw some consequences. And I guess the one I want to mention first is elliptic regularity. And this says that, let's apply it to the signature operator. If the signature operator applied to something gives us something else, which happens to be smooth. And okay, we have discussed to what kind of function sections of the form bundle we can apply the signature operator, but clearly we can apply it to all C1 sections. The differentiate ones can go beyond that even. Nonetheless, even if a priori is only C1, if the part D of F is smooth, then F has to be smooth as well. There's no way. And even better, morally, if this is k times differentiable, then this is k plus 1 times differentiable. Now this is not precisely true in the sense of differentiability, we know it, so we have to talk a little bit about the right version of differentiability and formulate that, which is the first to identify. So anyway, so I thought I'd do this in my crash course and analytic properties of this operator. Even better, so that requires a definition. We define quickly solidus spaces. So there's one house now for each non-negative integer. Okay. So different forms, so whatever your sections of your manifold are. This is going to be a Hilbert space. We get it by completing the smooth differential forms with compact support. This is an appropriate norm. So I only have to write down this norm. There is a little choice in the actual norm. The abstract topological vector space you get is always the same, but you have choices in this precise norm. So you can choose the one which is most convenient. Let me give one which is convenient here. Using the signature operator and the fact that it's elliptic, we can define the norm, if you have such a omega, to be the WK norm omegas squared, just define it to be do it is to sum the L2 norm to the L2 norm of applied the signature operator k times. And then take the L2 norm. So with this little surprising definition, we get new norm clearly. If k is equal to 0, this is just up to scaling the L2 norm. So typically I maybe should have divided by 2 to get the L2 norm back in that case. Alternative, just to show you that there's more ways to do that, we could take like a different norm where we sum over the L2 norms of all powers of the signature operator from 0 to k. And the more traditional version sum over L2 norms of just all derivatives up to degree. So all mixes of derivatives in all possible directions. This makes best sense if your vector space, your manifold, is Euclidean space, so that you know what are your directions, so that you get a finite sum out of that. But you can generalize that to manifolds using local descriptions and a partitional unity trick to get this done. So there are really many different ways to define that. But you see, the higher k is, the more differentiability is built in. Because you clearly have derivatives up to order k, all derivatives up to order k available just by completing with the spectrum norm, which allows to take these derivatives. And the regularity now says that, so what we always have, call this A, this is the differential operator of order E, then A maps Sobolev space order k to the Sobolev space order k minus d. And it does this continuously. And elliptic regularity implies some very strong statement. If you start with something and you end up in WK, we have to be in WK as well. Besides, form we apply signature operator something, and we end up with something which is in Sobolev sense k times differentiable, then automatically omega has Sobolev sense to k plus 1 times differentiable. Here's the right sense of differentiability, which is increased, just in contrast to what we expect if we differentiate. No, not in contrast, but it kind of cannot accidentally not increase differentiability in this operator. Others might. Right. So why did I introduce all of those? There is a second player which is very important, which is the relish era, maybe. Well, I mean, I hope we don't need that so much. Just to relate this kind of differentiability with a standard kind of differentiability, let me tell you that if you have a function or some section of our form bundle, which in the Sobolev sense is k times differentiable, it is indeed also differentiable in the usual sense of differentiability of functions we define locally, but we lose a little bit of differentiability. So if we want to end up in k times differentiable functions or forms, we need to be here in more differentiability, namely we need S to be bigger than the dimension of the manifold over 2. Okay? So there is not such a huge difference between this Sobolev differentiability and the standard one, but there is some. And you see, if we are in W infinity, meaning you require all of these non-fixes, then you also see. This is a continuous embedding of Banach space. And the other thing, which is something you do need, is the observation that if you take the closure with respect to some larger number of derivatives, of course you can think of the function also as sitting in the space where you compete with a smaller number of derivatives. Just have an obvious extension of the identity map to a continuous map, just because this norm is bigger than this norm, by definition. And what is not so hard to see is that this is actually inclusion. It doesn't quite follow directly from this completion definition. But the big thing is that this map between this Hilbert space and this Hilbert space is for n compact. Now we need n compact again. Is a compact homomorphism of Hilbert spaces. And let me just recall what this means. If you take the image of the unit ball, this is an infinite dimensional Hilbert space. The unit ball is not a compact subset of it at all. It's exactly compact with this Hilbert space. It's finite dimensional. Its image is a subset of this other Hilbert space, a different norm, and it turns out that it's pre-compact, its closure is compact. So something that is highly non-compact is squeezed down to something compact. Or equivalently, the map is the norm limit of other linear maps which have finite dimensional image. The finite dimensional image business is of course about the compact unit balls, and then take the limit. Okay. So that's a property we're certainly going to use. Classic, not going to prove it, but an exercise on N, the circle. This is a compact manifold. Things should look quite nice. We can work out the signature operator is actually the only operator which could it be, d by dx, or rather not y, d by dx. Prove this Greenwich lemma. And the best way to do it using our degree 0 forms, which are just functions on the circle. There is the Fourier transform, which transposes two functions on a circle to Fourier series. The one forms are also functions times dx, so we can play the same game. The differentiation becomes multiplication, and I guess we should be able to work out something on these properties for the circle case, and maybe pass on to the torus. Pn, and then to compact M using partition of unity and other tricks to localize the properties. Okay. So this is preparation. We're going to use this kind of properties in the next lecture. This time. Right. Another property of the signature operator. Say on a complete M, the signature operator goes from forms, let's say compact support, M to self. So these are smooth forms of compact support. And of course, these lie by passing the completion inside L2 forms on M. So that's something analysts like to do. It's very useful. We can really think of this operator as an operator from L2 to L2, but its domain of definition is a bit smaller than all of L2. An unbounded operator with a not full domain. And it turns out that this operator has a unique self-adjoint extension. Extension just means you make the domain slightly bigger, and self-adjoint means symmetric for the inner product, but in such a way that we can't increase the domain at all without screwing up things, essentially. Let me not define this technically, but there is a precise technical definition of self-adjointness, which is a bit better than being symmetric. I mean, this is equal to its formal adjoint. It's just by definition, because we added an operator as adjoint. And adjointing twice gives you operator back. So this is prime. It's not the adjoint in this sense. Symmetric. Actually, we also know what the domain of that is. Coming from electricity, the domain is the first double left trace W1. And that is good news. That's also not entirely trivial to prove. That's good news because if you have the self-adjointness property, we have the functional calculus available. Therefore, functional calculus is available. We can take bounded continuous functions on real life, and we can substitute f a d into f, and we get, if we start with a bounded continuous function, we get a bounded operator on the Hilbert space. And that is a star homomorphism, where here we have the multiplication and the complex conjugations to make this a star algebra, C-star algebra, and that is composition and the adjoint, which make this a star algebra. And it's also okay. So you will play a lot with these functions of the signature operator, and we'll do it even more than with bounded functions, with continuous functions which vanish at infinity. And so no exercise here. Leave this out, but we can use special description of this operator using again Fourier transform. So right. F of D as, well, this depends on the definition of the Fourier transform factor. Now, I want to do a Fourier inversion formula. So, how would f of a function look like in terms of Fourier inversion? Huh? You don't remember? Who remembers? You? Your neighbor? So, Frank, it's again you. 30 years ago, but you passed the exam. Woody?
E to the power IB psi times the Fourier transform of function
F.
of
Right,
psi.
so f of something is up to this factor, f hat of the same something, times e to the I, when f is e. And then our argument here is d, so this has to go here. Yeah, that's how it. Now, this gives us this mysterious operator e to the itd, which is defined because it's d of a bound function on the real line, so you don't have to worry about that one. I'm stopping with the properties of this thing. Okay, where d is definable via the functional calculus. Also has the property of being the unique solution of the wave equation. So, and then think of T goes to e to the itd as a map from the reals to unitary operator. Turns out that's an operator group. Some of the analysts call this just a homomorphism with additive group of the reals to unitary operators on the Hilbert space. And if we differentiate this, we get back e times e to the itd. There's a little subtlety here. This is not a bounded operator, and this differentiation as, let's say, via difference between the limit of difference quotients doesn't work for every vector in the Hilbert space, so the domains really work out to be the right ones. Anyway, so that's just a bit of background information. This goes into this, so it's a nice operator family which exists. This integrals exist as long as f hat is not too terrible. And the main point why I'm happy, why it's very useful to write this like that is that we have the unit propagation speed. So that's another year of it, and it goes back to Chernoff. We're still in the case where that's complete Riemannian manifold, all works in this generality, and it says that e to the ITB, if you apply this to some omega, we take a section of the form bundle, we apply its operator to it, we look at the support of this function. Right? If we think about propagating, we can take a function and we look at how much it spreads. That's what propagation means. So we compare the support after applying the operator to the support of the function we started with. Now that's a certain subset of our Riemannian manifold, where this function is non-zero, it's closure. And in Riemannian manifold, we can take R neighborhoods of a set. Every point which is at most distance R from that, so we can also take the T neighborhood of that set, called that UT. And the unit propagation speed means that the e to the ITD operator in the wave operator spreads at most by multiplied with T. So again, we have here the support, here is omega, and then that's multiplied with T, that. And inside this is the support of e to the ITD. And as a consequence, if the support of f hat, we call that the function on the real line, is contained in minus r, so if you take an f hat, which has compact support, then in my Fourier inversion formula, we integrate with a non-zero weight, non-zero cofactor, only operators which spread the support of the function at most by r, right? Because t as a value is always smaller than r, and so the whole thing spreads support at most by r. Get support of f of t omega contained in R neighborhood or omega of the domain. And this is called the finite propagation property, which we're going to use a lot in the next lectures. And I guess this is a nice place to stop. And of course, everything which was not proved is exercise.
Are there any questions?
Thomas, you have some more questions for us.
I think trying to prove the fine propagation is a nice thing, but you better do it with the case. It's not easy to do it on the nose. I mean, just so. Okay. But then he also mentioned that the fine propagation of this wave is something you expect. Right? The typical wave should travel with some speed, and that's exactly what's happening in the mathematics describing wave phenomena. Waves travel with the speed of wave.
Basically, to the sample there.